Modern enterprises possess more operational data and visualization software than ever before, yet executive trust in these generated reports has reached historic lows. Deploying a new dashboard tool creates a new graphical interface for an organization, but it does not, by itself, resolve an underlying lack of intelligence. Business intelligence is not a software purchase. It is the result of specific architectural choices. The lack of trust often stems from metric drift. This occurs when siloed departments apply their own mathematical calculations to the same business concept. Marketing might define revenue based on leads, while finance defines it strictly through processed invoices. These isolated definitions mean conflicting reports inevitably hit the executive desk at the same time. Leadership is forced to spend executive meetings debating whose numbers are accurate, resulting in a state of analysis paralysis. This illustrates the limits of diagnostic BI, the practice of spending weeks trying to explain what happened in the past. To remain competitive, organizations require accurate, real-time data that supports immediate action. Enterprise analytic systems fail at the data definition level. They break down long before a chart is ever rendered on a screen. To address metric drift at scale, organizations require a governed 6-component architecture. This environment relies on the synchronization of 6 distinct layers: data sources, integration, storage, analytics, visualization, and data governance. Moving to this model enables anticipatory BI. Instead of just reporting historical events, the system uses current data to identify patterns and suggest specific strategic adjustments. We will now construct this architecture from the ground up to demonstrate how a reliable reporting environment is manufactured. Establishing these 6 foundational layers is the prerequisite for safely deploying artificial intelligence and self-service analytics across a workforce. The foundation collects raw data from APIs, CRMs, and ERPs, pushing streams into a central warehouse. Cloud architectures use an ELT model: extract, load, transform, loading data first, then formatting internally. Automated filter gates scan for freshness, completeness, and referential integrity, ensuring mathematically sound data. When these automated checks are absent, incomplete or corrupted records enter the data warehouse. Downstream artificial intelligence tools then ingest this flawed information as the baseline for their logic. Sophisticated algorithms operating on corrupted raw data produce confidently wrong insights. The mathematical processing is flawless, but the conclusion is false because the input was compromised. Direct data pipeline reliability and upfront quality monitoring are the absolute requirements for any functional analytic system. The semantic layer is the most critical component of the 2026 stack. It serves as a validation layer that locks into place directly above the data warehouse to intercept every query. This layer centralizes all business logic in one location, outside of any individual visualization software. Developers use code-based languages like LookML or DAX to define exactly how a metric is calculated for the organization. For governance, every metric requires 4 documented attributes: mathematical calculation, data grain, refresh rate, and a designated human owner. This centralized code replaces the legacy practice where analysts would manually insert custom formulas into individual spreadsheet cells. The semantic layer also enforces role-based access control, or RBAC. RBAC is a security protocol that assigns data permissions based on an individual's job function. These security rules follow the data automatically. Whether the information is viewed in a web portal or a mobile app, the semantic layer restricts access based on the user's authorized role. Defining metrics once at the semantic level ensures that every department uses identical mathematical logic, removing conflicting numbers from the decision-making process. Once definitions are standardized, an AI agent layer can be applied. These agents scan the governed data streams to detect patterns that are often invisible to manual inspection. This allows for 2 levels of advanced analysis. Predictive analytics uses historical data to forecast future trends, while prescriptive analytics suggests specific actions to improve those outcomes. In real time, anomaly detection algorithms monitor the expected baseline of a metric. If supply chain volumes are predicted to drop, the issue is flagged before it impacts the current operations. A prescriptive agent can then evaluate the bottleneck and suggest a specific inventory reroute. It identifies which units to move between warehouses to maintain availability while minimizing expedited shipping costs. These agents can only operate reliably when the underlying semantic definitions are flawless. Without governed data, an autonomous agent will pursue the wrong goals with perfect efficiency. A governed semantic layer allows AI to generate these prescriptive recommendations as a direct extension of existing historical analysis. The final layer forks to serve different user needs. Technical users require deep dive modeling interfaces, while business managers need streamlined, accessible views. For non-technical users, natural language processing, or NLP, allows for conversational queries. By typing a plain English question, the system uses its governed logic to answer, instantly generating an accurate bar chart. Highly technical data modeling and complex SQL, the structured query language used to communicate with databases, are reserved for data engineers and analysts. Ungoverned self-service creates a significant risk. If non-technical users attempt to combine incompatible datasets without a semantic layer, they will reach mathematically impossible conclusions. The semantic layer serves as an invisible guardrail for these business users. They are free to explore and visualize data without the risk of altering or breaking the core logic. This architecture democratizes data access across the enterprise without compromising security or mathematical accuracy. Business intelligence is not a linear project. It is a continuous, closed loop. The insights discovered at the visualization layer must inform how raw data is collected and prioritized at the base. A modular design allows the system to ingest new data sources without a total rebuild. In this environment, value is measured by active daily adoption. A dashboard that is never opened provides no operational benefit, regardless of its complexity. Organizations must actively manage dashboard sprawl. Reports that no longer support a specific business decision should be pruned to ensure the system remains focused. Maintaining this loop requires ongoing data literacy training. The workforce must understand how to interpret these visuals and apply AI-driven recommendations to their specific roles. Even the most advanced semantic architecture provides no business value if the human workforce does not understand or use the output. The 2026 BI model operates on a strict chain of dependency. Autonomous action requires governance. Governance requires quality, and quality requires reliable integration. This structure enables a human-in-the-loop model. Human personnel shift from the manual work of searching for data to a role of strategic oversight, where they audit and approve autonomous execution. Companies utilizing anticipatory BI can react to market shifts in real time. Organizations lacking this architecture remain stuck debating historical spreadsheets, while the opportunity to act passes. Leadership must audit their current state. Does the organization rely on a governed semantic layer or a collection of disconnected dashboards with conflicting metrics? In the autonomous enterprise of 2026, governed data functions as the central engine driving continuous and long-term strategic growth.